are not uploaded or recorded. So these things are optional, but the idea is those who actually show up to it benefit. Okay, I'll record it, but those who are not actually here, not taking part face to face, are not going to be of much use to them anyway. Okay. No, Mariam, that's not the point. The point is those who want to take advantage of it should actually show up. I'll upload it anyway, and I'll have it available on Moodle after this, so that's fine. Okay. I'll upload it. But the point is, you don't get as much benefit if you're not actually here. There are no finals at the time of scheduled lectures. This is actually a scheduled lecture, Rayan. Anywho, let's keep going. I'll upload it anyway. I'll have it public, open. Anyone can take a look at it. You can send it to your friends. I'm just saying they're not going to benefit from it as much. Anyway. Okay, so the entire idea is you have something on the top of a ditch, and then it goes down. So it is somewhere here, right next to a crater. There is a wheel. Its radius is 25 centimeters, so 0.25 meters. And it starts rolling all the way down to here. And the question is, when it reaches this location, what is its velocity? Well, we use the concept of conservation of energy. Okay. At the top, there is only one type of energy, mgh, potential. At the bottom, they have mgh, they have half mv squared, and they have half I omega squared. Okay, so rotational kinetic, translational kinetic, and potential energy. Okay. We know that. What other information do we know? We know that ICOM of this wheel is equal to, this is a disk, so it is mr squared. We know r equals 0.25 meters. We know the height equals 25 meters from the question, right? And we know the mass is equal to 5 kilograms. That's all we know. Okay, so we start putting it in. Now, something to bear in mind is that this is on Mars, not on Earth. So G is not 9.81. On Mars, G is equal to 3.71. Yes, if you have a question on another planet in a test, you will be given the value of G. Okay, or you will be given enough information to be able to calculate the value of G. Okay. So let's write it down. mgh equals. Now this will go to 0 because here h is equal to 0. H equals 0, h equals 25. Half mv squared plus half I omega squared. Now I don't know what omega is, but I know omega is equal to v over r. So I will rewrite this as half mv squared plus half I v over r all squared. Put in the numbers. 5 times 3.71 times 25 equals half times 5 v squared. I don't know what v is. This is what I want to find. Plus half I is equal to mr squared. So 5 0.25 squared v squared divided by 0.25 squared. Okay, 0.25 squared goes with 0.25 squared. And I end up with 5 times 3.71 times 25, 463.75. So I end up with so V is equal to 463.75 divided by 5 square rooted, which is 9.63 meters per second. Is that what the book gets? Yep. So that is example 11.3. Yeah, you can cancel the m since you have m everywhere, but I was too lazy to do that, so I just substituted it and then divided by it. It's the same thing. But you are correct, since I have an m here, an m here, and so basically I have m, I can get it over with in the first place. And that would be even easier, actually. Yeah? Okay. Let's see, example 11.6. لا ما في ريان. Okay, 11.6. Angular momentum of a robot arm. A robot arm on a Mars rover like Curiosity, okay, the one we had before, is 1 meter long and has forceps at the free end to pick up rocks. The mass of the arm is 2 kilograms and the mass of the forceps is 1 kilogram. The robot arm and forceps move from rest to omega equals 0.1 pi radians per second in 0.1 seconds. It rotates down and picks up a Mars rock that has mass 1.5 kg. The axis of rotation is the point where the robot arms connects to the rover. What is the angular momentum of the robot arm by itself about the axis of rotation after 0.1 seconds when the arm has stopped accelerating? What is the angular momentum when it has the Mars rock and is rotating? When the arm does not have a rock, what is the torque about the point where the arm connects to the rover when it's accelerating from rest to its final angular velocity? Okay. So okay, so here is the system that we have. We have a pivot point. We have a rod with a forceps at the end and a rock. This is 1 meter length. So to look at the moments of inertia, I need to do some approximations. I will say the rod is I'll look at the moment of inertia for the rod about rotating about the end here. Okay, so I rod will be equal to 1/3 ml squared. For the other things, okay, for the forceps and the rock, they are small compared to the arm. So I'm going to do them as if they are point masses. So mr squared, mr squared. I total equals mr squared plus mr squared plus 1/3 ml squared. The arm weighs 2 kilos. Forceps is 1 kilo. And rock is 1.5 kilos. All right. This is all the information that I need at the time being. Oh, yeah. And omega equals 0.1 pi radians per second in 0.1 seconds. So I drew something. I drew a sketch. I wrote down all the information. I converted them to wherever I need conversion. Okay, they're all in the correct units. Now I can start to do the question. A. We want to know the angular momentum of the rod with the forceps. Right? Let's see. What is the angular momentum of the robot arm by itself? So without the rock. That is fine. So A. L equals I omega. My I will be that of the rod and the forceps. Okay. So it's going to be mr squared plus 1/3 ml squared, which is which will give me, since we're using them as point particles, they're all going to be at 1 meters. So it's going to be 1 plus 1/3 2 1 squared. So that's 2/3 plus 1, and that is 1.67 kilogram meter squared. This needs to be multiplied by omega. So 1.67 times 0.1 pi will give us it will give us 0.17 pi and the units will be kilograms meter squared per second. Part B, what is the angular momentum when it has the Mars rock in its forceps and it is going upwards? Well, it's the exact same calculation, but now instead, the direction here is k given by the right hand rule. Okay, we do the exact same calculation, but now my eye also has an extra component because there's the stone. So this will be equal to mr squared plus mr squared plus 1/3 il squared omega, and as the book says, it will end up with 0.32 pi. Also in the k direction. Yes, Ryan? Yes, you have the formula sheet uploaded on Moodle already, which is available for use during the final and during the midterm and during all quizzes. And everything is in it. No, you have a formula sheet with all the eyes. You pick out the eye that you need to use. When the arm does not have a rock in the forceps, what is the torque? Well, torque is dl by dt. Okay. And that is equal to I alpha. And we can calculate the torque. It's given in the book exactly. So I'm not going to do the same calculation in the book again to be able to do more examples. Noor, inshallah, it is about the same level as the midterm. Marwan, two long questions. Maryam, L is angular momentum. So just like in translational motion, we had P equals mv, which we called momentum, and which we said is conserved, right? Now the angular equivalent of it, okay, is L, given by I omega. We call it angular momentum, and it is also conserved. Okay. So there's no easy way to conceptually understand what L is. Okay. It is the angular part of momentum. That's the only way to explain it. So this is one of the, let's say, not as beautiful sides of physics, or beautiful depending on your point of view. The more advanced you get in physics, the more things are described by mathematics. Okay, think of it as a language. um, think of it as a language. So when you first start learning a new language, every single word you hear, you start translating in your head to Arabic, right? So when I first started learning English, what time is it? ساعة كم الحين. Everything I would translate in my head to Arabic to understand. Now, what happens is over time, you start getting used to that language. And after a while, there are some things that you can explain in one language that you cannot explain in another language. Now, for example, if you ask me what is the description of the time dependent Schrodinger equation for some simple harmonic motion in Arabic, I can't do it in Arabic because I simply don't know what is it in Arabic. Now, this is the same thing with physics. Initially, the things we study are things that we can catch with our hands and see on a day-to-day basis, and those we can describe using words, using props, using toys, using physical items. Over time, okay, as things become more and more difficult, the language of physics is mathematics. You end up just simply, talking mathematics. So if you go eventually to talk about, for example, something like electric fields or magnetic fields or quantum wells, there is no words to describe it. It's just math. It's just a bunch of equations. Okay. So that was example 11.6. So section 11.3, Dina says في شيء غريب. So ايش هو الشيء الغريب في هذا السكشن دينا؟ Hmm. Okay, I'll take a look at the homework problems. We'll do a couple of them. Some students have asked for them. But to start with, okay, Dina, in chapter 9 and chapter 10, we spoke about conservation of momentum. We said P before equals P after, and then we said M1 V1 equals M2 V2, and we used this conservation to find different velocities of different things at different times. Okay. Were you okay with that? Okay. So 11.3 is exactly this, but for rotational items. Okay. For rotational items. It says L before equals L after. I1 omega 1 equals I2 omega 2. Okay. It's the exact same idea which we are used to seeing on a daily basis. Okay. but on an angular level. Let me see. I have an idea in my head. Let me see if I can find a video to describe it. Um, 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 um. Okay, let me share my screen, and hopefully. So, Mariam, I'm explaining angular momentum generally because a few students are having difficulties with it conceptually, not as in, not with specific problems. So, YouTube's gonna have a field day with me showing 3 videos, and it's gonna have a fun time with this whole monetizing thing. Okay.
When I hold the spinning wheel, nothing crazy happens. But when I flip it, I spin. Flip back, and I stop. Flip it, I spin. So the question is, why am I spinning? So I have to force the wheel to turn over. Now Newton's third law says that for every force, there's an equal and opposite force acting as well. So when I force the wheel is applying force equal and opposite onto me, causing me to turn. So the same thing applies when I'm on the ground, but the friction between my shoes and the ground stop me from spinning. So another way to explain what's going on is through conservation of angular momentum. Now, angular momentum is something that tells you how hard it is to either start or stop something from spinning. And it depends on 2 things. 1, how fast it's spinning. We call that the angular frequency. 2, its shape, or what we call the moment of inertia. So this wheel is rotating counterclockwise. Now I'm going to teach you a trick. So get your right hand, and I want you to curl your fingers in the counterclockwise direction. And you see that your thumb is pointing upwards. We'll call that the positive direction. So see, this wheel has positive angular momentum with a magnitude of L. Angular momentum is conserved. That means that as long as there are no outside forces, the total angular momentum of the system always stays the same. So when you flip this thing over and do the right hand trick, your thumb points down or in the negative direction. So the angular momentum of this wheel is now negative L. So the whole system, me, the turntable, and the wheel starts out at negative L. But when you flip the wheel now has positive L. So the whole system needs to stay at negative L because of conservation of angular momentum. So I need to spin with angular momentum of negative 2L. That's why I spin the other way.
Okay. So the idea is, just like with translational momentum, we had a 0 change in angular momentum in the absence of external forces. It's the same thing with angular momentum. Now, if initially I am not moving but I have something moving in this direction. Then I put it the other way around. Okay? I flip it, just like you saw in the video, and now this thing is moving in the opposite direction. Now, to have the same value of L that I had here, instead of being still, I need now to start spinning in the opposite direction, so that the total amount of L I have in the system is the same. Okay, now the rotation speed, the angular velocity, the speed of my rotation for the red line and the black line does not have to be equal. Okay, because remember, me as a person, I have a different eye than the initially rotating wheel. Okay, but the multiplication, the product of them need to be equal. So say, for example, initially I am standing on that turntable thing without anything moving. Okay, so I am not moving and the wheel is not moving. What is my total L here? So my total L here is equal to 0 because this is not rotating, omega equals 0. This is not rotating, omega equals 0. So my total L is 0. Now, if this outer thing starts rotating in this direction, it will have L equals minus I omega, which necessitates that the thing on the inside needs to go in the opposite direction so that its L is equal to plus I omega, so that when I do I omega of object 1 plus I omega of object 2, my result would still be equal to 0, just like before. Okay, so let's do this example, 11.7. Coupled flywheels. A flywheel rotates without friction at angular velocity initially of 600 revolutions per minute on a frictionless vertical shaft of negligible rotational inertia. A second flywheel, which is at rest and has a moment of inertia 3 times that of the rotating flywheel, is dropped onto it. Okay, so see, this one has I naught, this one has 3 I naught. Okay, this one has an omega naught of 600 revolutions per minute, and the top one is not rotating. Now, because there's friction between the surfaces, the flywheels will very quickly reach. Yes, I depends on the R. You are correct, Mariam. They reach the same rotational velocity, after which they spin together. So initially, we say we use the law of conservation of energy, conservation of angular momentum, to determine the angular velocity omega of the combination. And then we want to know what friction of the initial kinetic energy was lost when the two flywheels came together with friction and became in the same speed. If the R changes, then the I changes and the omega changes as well. So the conserved quantity is not I, is not omega. The conserved quantity is L equals I omega. Okay? So if I goes up, omega will come down. If I goes down, omega will go up. But L will remain the same. If R, for example, decreases, this might decrease, which means we will end up with this situation. Or in some instances, it might increase, which means we'll end up in this situation. Okay? So, okay, it's the same with translation. Many times students get confused by some of the concepts. P equals mv. M is not conserved, V is not conserved, P is conserved. Yes, in day-to-day things that we do, okay, M is usually also conserved. So if V goes up, P goes up. If V goes down, P goes down. Okay, because in day-to-day things, we don't usually have M changing, yeah? If I weigh 100 kilos, I'm a fat person, I'm still gonna weigh 100 kilos no matter what happens, unless I diet. Okay, but when you talk about advanced physics, things going at the speed of light, weird things happen, mass is able to change. Okay, but the concept is the same. P is the conserved quantity, not M, not V, but the product of M and V. Okay, let's do this. So we have no external torques acting on the system. Okay, the only thing that happens is one is rotating, the other is not rotating. We put them together. Friction is between them, so inside the system itself, internal torque, and they start rotating together. So I naught omega naught. Why am I unable to choose this? Okay, this is the initial L of the rotating thingy. Yeah, I omega. I naught omega naught is equal to, later on, I increases. I naught plus 3 I naught, because that top thing is heavier, omega. Now we can immediately say, okay, this is what happened. We had I omega, then we had I omega. They need to be equal. Okay, since this went up, this has to go down. And we'll see whether this happens or not. Initially, it was at 600 revolutions per minute. Okay, so we do I1 omega 1 equals I2 omega 2. We solve for omega, okay, and we get 150 revolutions per minute. So omega naught divided by 4. So indeed, its velocity reduced to a quarter of what it was. Before contact, only one flywheel is rotating. Okay, so part B says, okay, how much kinetic energy did we lose because of what happened? Well, the rotational kinetic energy before was half I omega squared, right? The final kinetic energy is still half I omega squared, but now I has changed and omega has changed. Okay, so initially I had half I omega squared. This was I naught, this was omega naught. Finally, it is still half I omega squared, but my I is now actually 4 I naught, and my omega is actually a quarter of the initial omega, like this. Right? Now these two are not equal. If I put in the numbers for this and I put in the numbers of this, I will not get the same numbers. So my energy is not conserved. And if I actually do it, okay, I will find that my final kinetic energy is a quarter of my initial kinetic energy, which means I lost 75% of my energy during the coupling. From radian to revolution or revolution to radian? So revolution is 1 round, which is 2 pi r. Okay, we actually did this. Let me bring up the slides because there was a nice so 1 revolution, when I go 1 revolution, I go 360 degrees. Okay, this is how I remember it. 1 revolution, 1 round is 360 degrees. Which means I am going 1 circle of circumference of 2 pi r. So 360 degrees, 1 revolution is equal to 2 pi r divided by my radius. Which means 1 revolution is 2 pi radians. 1 radian is about 57.3 degrees. So if you have revolution and you want to go to radian, you go 1 to 2 pi. 10, for example, is how much? So you multiply it by 2 pi. So revolution to radian, you multiply by 2 pi. Radian to revolution, you divide by 2 pi. Ahmed, K equals half I omega squared when it's only rotating. Okay, when it's only rotating, it's half I omega squared. When it's rotating and moving translationally as well, it's half I omega squared plus half mv squared. Okay, so basically what's happening is when it's rotating, it's half I omega squared. When it's moving only, it's half mv squared. When it is moving while rotating, like a football, you add the two. You have this plus this. Okay. So what your friends answered you how to do it, but generally speaking, when you want to change units, okay, what you do is you change them one at a time. Okay. Say for example, I have 20 kilograms meter squared divided by per minute. And I want to make it grams millimeter squared per day. I don't even know what is this thing unit of. Okay, I just made it up. How do I go from here to here? Well, I write my 20 and then I ask myself, if I want to go from kilogram to gram, what do I need to do? I need to multiply by 1000. So I multiply by 1000. I need to go from meter square to millimeter square. What do I do? Well, from meter to millimeter, I multiply by 100. So from meter square to millimeter square, I multiply by 100 again. So 100 times 100. Okay. Yep, 10,000. But I don't memorize 10,000 because otherwise I will just spend so much time trying to memorize so many different, going. So for example, meter cubed to millimeter cubed, it's a million. Just trying to memorize, all these numbers is a bother. So I only memorize meter to millimeter, 100. Simple. Square, do it twice. Cube, do it 3 times. And so on and so forth. Now from minute to day. Now from minute to day, what do I need to do? How many minutes are there in one day? One day equals 24 hours. 24 hours, each one of them has 60 minutes. So I do. So what do I do? One 440. Do I multiply by 1440 or divide by 1440? I divide, right? So 1 minute divided by 60, that's for hour, times 24 hours. Which means I will end up with, sorry, this was supposed to be in a different color. So what I will end up with is 20 times 1000 times 100 times 100 times 60 times 24. And I will add up. Yeah? That's one way to remember it. Okay? It's violent, but it's one way to remember it. And I will end up with 2.88 times 10 to the power 11 gram millimeter square per day. Okay. Yeah. Yes, I multiplied everything. I just didn't write them on one line because بتصير زحمة. This is what I did. There's no division. Okay, what? Did I make a mistake somewhere? I did. Yes, it's 1000, 1000, not 100, 100. Right? So this should be to the 13.
دكتور
Yes.
ما المفترض نضرب في 60 في 2 في 24 لأنه يعني هو الملي يعني أو بير داي صح؟ الداي هنا بتكون تحت فنعوض الداي فيها اللي هو 1414
for 1440. ايوه 60 times 24 is 1440 صح.
يس انزين المفروض يعني مكان الداي يعني ما المفروض تطلع لي فوق
كيف؟
يعني دكتور شوف المفروض بيكون هذه 20 ضرب، يعني ضربنا صح اللي فوق، حولنا الملي اللي فوق،
مهم.
بعدين تحت ما المفروض نسوي 1 minute over 60 multiply by 24، المفروض بس 16 multiply by 24.
طيب أنا راح أجاريش في هذا الموضوع and let's see if it works or not. Okay.
اوكي
We have 1 minute وبعدين تقولي اضربه في 1440 صح؟ فيطلع لي الجواب 1440 يوم. هل هذا صحيح؟
لا لا لا
في
دكتور، ما كذا أقصد.
1440 يوم في الدقيقة؟
لا ما أقصد كذا كان. شوف
أيوة.
دكتور، مثلا اللي إذا جينا نحلها بالطريقة العلمية بيكون يعني هذا اللي معطينا إياه، تو هي بير مينت ولا بير داي؟
هي كانت بير مينت واحنا نحولها إلى بير داي.
ليش؟ أنا العكس على بالي داي نحول.
لا هي
شكرا
كانت
شكرا.
مينت ونحولها لدي، فعشان كذا قسمنا قسمة القسمة ضرب. اوكي alright. وانا ليش مسحتهم؟ خليهم. يس وعد. اي واحد مال التوتوريال. Okay, let's see. Chapter 11, question 32. 3 people asked for this question, so let's do that first. Close this. So okay, question 32. And then let's see what other questions we have. I'm trying to finish as much as possible in the next 15 minutes. 33 is similar to 32. (42) needs vector cross products twice. 43 is interesting. Okay, let's do one at a time. What? This is a conservation of momentum. M1 V1 equals M2 V2. ما فيها تصادم. It doesn't need to be تصادم. هم ما يصطدموا. They are in opposite directions. So you have 4 divided by 9.81 times 15 meters per second equals 720 divided by 9.81 V2. Okay. And أيوة. So if you do 4 times 15 divided by 9.81, actually 9.81 you can simply ignore in both areas. So you do 4 times 15 divided by 720, his velocity would be 0.083 meters per second in the opposite direction. Okay. Now let's do 32 and then we'll go do 42. I think those would be the last 2 questions we have time to do today. But let's see. Okay. Okay, Wa'ad, we can come back to this once we finish with chapter 11, since we're focused on chapter 11 at the moment.
Doctor, question 32 in this chapter في هذا في friction فإحنا اللي سويناهم بدون frictions في الماضيات.
Yeah, so let's do one with friction.
بس كاتبين هو roll without slipping يعني الفريكشن مال إيش؟
خلينا نشوف. A solid cylindrical wheel of mass m and radius r pulled by a force F applied to the center of the wheel at 37 degrees to the horizontal. If the wheel is to roll without slipping, what is the maximum value of F possible? The coefficients of static and kinetic friction are mu s 0.4, mu k 0.3. Okay, so every time we do the question, we say rolling without slipping. Rolling without slipping assumes something. Assumes that whatever value you are doing is within the limitation of friction. Okay, because if it's more than the limitation of friction, you will end up slipping, right? So from the lecture, I'm going to use a result that we derived in the lecture. Okay, But first, I need to check something. Again. Yep, this is given in your formula sheet, so I can use it directly without derivation. So, from your formula sheet is a result that we derived in the lecture. We said that roll without slip means ACOM equals G sine theta 1 plus I over mr squared. For a cylinder, which is what we have in this question, ICOM equals half mr squared. So I will substitute that, and I will get A COM equals G sine theta 1 plus half mr squared divided by mr squared. mr squared cancel. 1 plus half is 3 over 2, which means I get 2G sine theta over 3, which is really, really simple. لا القانون ثابت حسب الشكل الاي بيتغير فيه. Okay. Now let's draw a free body diagram. We have this result to work with. Okay, let's draw a free body diagram. If this is my cylinder, okay, this is my F. This is F cosine 37. This is F sine 37. And I will have friction. Right? I will also have the normal force. And I will have gravity downwards. This is my free body diagram. So let's write it down. If I look okay, so the road here is straight, our force is at an angle, which makes the problem a bit easier. So the force equation along the y-axis is normal force plus F sine 37 must be equal to mg, because we don't want it to fly, we want it to roll. Right? So I'll just rewrite it to be n equals mg minus F sine 37. In the horizontal, this is in the y-axis. In the x-axis, f cosine 37 minus, since it's already moving, mu k, normal force, is equal to my MA. I will substitute this n here. I will get f cosine 37 minus mu k mg minus f sine 37 equals MA. Now A, I have from back up here. I will substitute this back in. So f cosine 37 minus mu k mg minus f sine 37 equals m 2g sine 37 divided by 3. Now I know mu k from the question is equal to 0.3. Correct? So I know mu k is 0.3. So I can simply substitute here 0.3. I know my mass. What is my mass? Oh, I don't know what my mass is. So I'll just keep it this way. But my mass is a constant. G is a constant. The only thing I need here is F. So if I rearrange this whole thing, I will get cosine minus sine, cosine plus sine. So I will get F equals 2 mg sine 37 degrees plus 3 mg, well, 3 times 0.3 will be 0.9. So 0.9 mg divided by 3 cosine 37 degrees plus 0.9 sine 37 degrees. Okay. Here is the minus.
دكتور أقصد تحت 3 cosine 37 minus 0.9 sin 37. ليش سويناها positive plus؟
Minus. Or did I make a mistake somewhere? mu k عالية because it's already moving. Mu s is only when it's not moving. Fs as in friction force. There we go. No minuses. And this will be equal to, so I'll just take the mg out. So 2 sine 37 plus 0.9 is equal to 2.1036 mg divided by 3 cosine 37 plus 0.9 sine 37, 2.9375. And this means 0.72 mg. Yep. So we did this from first principles, step by step. So Slater and Chegg are two websites that are, and there's another one called Turnaby, Appleby, something like this. They're good websites to revise homeworks, to do things, but I would not take them as a gospel. They do make mistakes sometimes. Okay. Turnaby, Appleby, something like في B في السالفة. Problem solutions Turnaby. Nope, can't find it. Appleby. I can't find it. If I found it, I'll tell you. ما جت تطلع لي الحين. كان في شيء بي في السالفة أتذكر. I'll upload the thingy. Okay. Right. I'll do 42 since it has a nice vectorial thing. Yes, Rayan. It will be in Moodle and it would be using a PDF. Okay. كيف يعني ما يسلم؟ أنه people uploaded and it didn't go through? Noor, Gmail is impossible. I will end up having 300 emails. Times 2 questions, so 600 emails. It will be physically impossible to go through them properly. Let me see, Rayan. I'll try to ensure there is some sort of mechanism. Okay. But usually when you upload something in the Moodle, it should give you a confirmation that you uploaded something. But I will double check nevertheless. Okay. So by tomorrow, inshallah, we should have the paper ready, and then we're going to be spending the next 3-4 days basically debugging and troubleshooting, hopefully, so there are no technical issues during the actual test. Okay, at a particular instant, a 1 kilogram particle's position is r2i minus 4j plus 6k meters. Its velocity is v equals minus 1 plus 4j plus 1k meters per second. And the force on it is 10i plus 15j newtons. What is the angular momentum of the particle about the origin? Well, Now, the angular momentum has two ways to calculate. One is I omega. The other one is R cross P. Now we're going to be using this one since we already have R and we have V and we have M. So we're going to be using L equals M R cross V. So let's write it down. Actually, I'm going to be doing R cross P directly. I have V, so my P is equal to be MV. Since M is 1 kilogram, so my P is simply going to be minus 1I plus 4J plus 1K kilogram meters per second. So L equals R cross P. Let us do our nice cross product. I, J, K. Minus 1. Nope, it's R cross P, so first R. 2 minus 4 plus 6 minus 1 plus 4 plus 1. Okay, so let's do it. For I, we will get minus 4 plus 4 times 6. Nope. I've already started doing mistakes. It should be AX minus BZ. So it should be minus 4 minus 4 times 6. For J, I will have I cross K. What is I cross K? Plus J minus J. Remember the rules. I, J, K, I, J, K, I, J, K. So K cross I is plus J, but I cross K is reverse, so it's minus J. Okay, so I will put minus J here. Okay, it will be 2 times 1 minus 6 times minus 1. Then K, I'll have I cross J, so that's again plus K. I will have 2 times 4 minus 4 times minus 1. So minus 4 minus 24, that will be minus 28 I. 2 minus minus 6, that's plus 8, but in the minus J direction, so we'll have minus 8 in the J direction. 8 minus plus 4, so 8 minus 4, that's 4. So that is plus 4 in the K direction. So this is my angular momentum. Now, part B is, what is the torque on the particle about the origin? Well, torque equals R cross F. So again, I, J, K. We have R, we have F, 2 minus 4, 6. So we'll have 2 minus 4, 6. And F is 10 plus 15, 0. Have 10 plus 15, 0. So I'll have I minus J plus K. I will give me minus 6 times 15. That's a big number. Okay. So I will have 2 times 0 minus, nope, sorry, minus 4 times 0 minus 6 times 15. 2 times 0, 6 times 10, 2 times 15, minus 4 times 10. لا ويش. لا 6 times 10, I'm confused. Four zero minus 615. 20 minus 610. No, ما العكس. We take this away, we take this away. 2 times 0 minus 6 times 10. Yeah, so we have A, B, C, D. It is AD minus BC. So 2 times 0 minus 6 times 10. Or 0 times 2 minus 10 times 6. Either way, it's 2 minus 60. Sorry, 0 minus 60. So we end up with 6 times 15 is 90. So minus 90i plus 60j plus 30k. And this is my torque. Yeah. So it is AD minus BC. Now, whether you do AD or DA doesn't make a difference, but it has to be AD minus BC. Part C. What is the time rate of change of the particle's angular momentum at this instant? So So time rate of change of angular momentum is equal to torque AZ BX minus AZ BX minus AX BZ, right? So we have I, J, K. This is A, this is B. Okay, this is AX, AY, AZ, BX, BY, BZ. We take this away.
دكتور،
أيوة.
ترى كلام دينا صح وكلامك صح، بس دينا شبه القاعدة الموجودة في الكتاب. هناك في الكتاب يعني يعني مباشر، يعني كاتبين المعادلة النهائية، يعني ما مسويين كذا يعني بين قوس مثلا سالب جي، يعني هم في الكتاب ضاربين مباشرة.
وين في الكتاب؟ أعطوني رقم الصفحة في الكتاب. في chapter الفيكتورز في الكتاب، يعني chapter 2.
ما أذكر أي chapter بالضبط، لكن هو يعني أنت لما تحل تسوي بالخطوات خطوة خطوة، فعادي بعدين يعني الناتج النهائي لو دينا طبقت الموجود في الكتاب يطلع نفس المعادلة آخر شيء.
دقيقة خليني أشوف. vector product. Okay. I see your source of confusion, Dina. I see your source of confusion. Okay. Okay, Dina, I'll come back to this in a second. Just let me finish part C and I'll come back to this because I know exactly where your confusion is. Okay, so part C of the question says, what is the time rate of change of the particle's angular momentum? So torque equals dl over dt. Okay. A second, did I make a mistake somewhere? Yes, I made a mistake. This should be 70. And they're changing what is, part C is asking you, what is the time rate change of angular momentum? By definition, the time rate change of angular momentum is what? Is torque, right? Correct? So my time rate change of angular momentum is simply my torque. This, nothing to do in part C. Now, I know exactly where your confusion is, Dina. So this is the rule that you are looking at in the book, right? Okay. While, yes, I know I'm presenting to everyone. Stop reminding me every 2 seconds. Cross product, cross product. Not this one. ما يبغى الوقت. يقول what is the time rate of change, not what is the time. What is the time rate of change? Time rate of change is torque, dl by dt. No. What is the time rate of change? Time rate of change means d by dt of angular momentum. So d by dt of L. dl by dt is torque, which is what we found in part B. Okay, so here is where your confusion is. In the book, you're looking at it, and it says AZBX minus AXBZ. I don't like that. You know why? Take a look. YZ, ZY, right? Means you are doing this, red, minus blue, right? So far, so good? Okay, now let's go to K. Leave J alone, go to K. Okay, AXBY minus AYBX, right? So again, it is red minus blue. Good? Now come to the J, the rule suddenly flips. It goes this way minus this way. And I don't like that. The reason they put it this way is because they want to keep it all positive. They want this to be positive, this to be positive, this to be positive. Okay, so here is when we did it in the lecture. Okay, these two lines of the white lines are from the lectures. Okay, so we did what we said was we get minus j because I cross k is minus j, AXBZ minus AZBX, which is the same order. 1 minus 2, 1 minus 2, 1 minus 2. Not going in opposite directions. Okay. So the methods give you the same result, okay, because they are the same thing, but the intermediate step is different. Okay. What I do is I say I have this, okay, and I just apply the rule one after the next after the next. Okay, so I have AX, AY, AZ, BX, BY, BZ, And what I do is, okay, I want the I, cross this out, do red minus green. Good enough? Good enough. Okay. Then we go to J. I'll take the J away, and I will do red minus green. Then I go to do the K, and I do red minus green. Okay, so it is consistent. At each step of the way, it is consistent. And the only thing changes is you're looking at IJK. Okay. Sorry, I have a call. Give me a second. Okay, I'm really sorry, but my next meeting is already here. They've been waiting for about 10 minutes. So I need to go. Okay. I'll try to have another session on tomorrow or Sunday morning, but I know you already have a lot of finals. Okay. So I think it is much more useful for you to try and revise for your finals rather than sit with me and do question by question. I've received quite a few of your emails. I will get back to you, inshallah, by the end of today. Okay, if you have asked for questions, solutions, or something, I will send it over to you. Okay. Again, I'm really sorry, but my next meeting is already here. I will see you soon. I'll see you soon, inshallah, and I'll reply to your emails as they come. Okay. Have a great day. No worries, that's my job, and I'm just hoping that it was useful for you and not a waste of time. Okay. See you around. I'll send an email about another office hour, or if you want a private office hour, just email me. Okay. في أمان الله.